Remember that a tessellation is a repeating pattern of figures that completely covers a plane without gaps or overlaps. Think tiles on a floor. Maybe you even look down at the floor upon which you're sitting or standing and notice what kind of tessellation pattern that is. In our school building, do you see what kind of shape that is? Write it down, maybe in the margin or somewhere on your note sheet. This that you're looking at right here is another tile pattern. This is called a regular tessellation because it's made with regular hexagons. Do you see the hexagon in this picture? 1, 2, 3, 4, 5, 6. 6 sides that are all congruent, and all the angles are congruent as well. So we have a regular hexagon. Notice in this tiled picture, there's no gaps anywhere and none of the hexagons overlap. I could trace an entire other hexagon and it would not overlap or leave a gap with the ones that are next to it. Now, how do I know if a figure can tessellate? Let's explore with angle measures why this regular hexagon will tessellate. So remember how we tell how many degrees the interior angle measure of any polygon has, any convex polygon. We use first the sum of the interior angles is n minus 2 times 180. How many sides or angles does a hexagon have? Hex is like 6, right? 6 sides. So this one, 6 minus 2 times 180, or 720 degrees. Now that's the total, all of them added up together, but there are 6 of them that are all the same. So each one interior angle is going to be 720, the total, divided evenly by those 6 interior angles, which makes 120 degrees. So each of these interior angles is 120 degrees. So notice the hexagon that's sitting next to this hexagon, the interior angle that's adjacent to it, also has to be 120 degrees. And if I look at that other hexagon that touches the first two, its adjacent angle, also 120 degrees. Well, notice as I trace those angles, what kind of shape that's making. From this point, we've got here, here, here. That's making a circle centered at that point where all these 3 hexagons are adjacent to each other, where they touch. Well, what is 120, 120, 120 all put together? If we add those adjacent angles, it makes 360. Why? Because to go all the way around a circle is 360 degrees. So to know that our polygon will tessellate around any point where the 3 angles will meet each other, will be adjacent, has to make 360 degrees. Another way to think about that, 360, is it divisible by the interior angle measure of the regular hexagon, 120? Well, if we do 360 divided by 120, we get 3. Not 3 point something or a fraction, but exactly 3. That means I can put 3 of those interior angle hexagon angles adjacent to each other without any overlaps or gaps. So I know it will tessellate. It comes out evenly when I divide it into 360, the degree measure for making a circle. Let's look at some other regular polygons, like a regular pentagon. Will it tessellate? Well, I could take these regular pentagons and move them around and try to see if I can create that tiled floor kind of thing, and I'm trying to, but I don't really see how I can get that in there. Now, I've already done this earlier to show you, no, it just can't work no matter how I try to put them together. I can put some of them together such that they touch, but ultimately I can't really find a way to get them into each other or next to each other such that there's no gaps or overlaps. I could put this one on top, but that's overlapping, and that's not allowed in a tessellation. Well, let's look at those interior angle measures. Remember that it's a pentagon. Pentagon has 5 sides or 5 angles. So when I do 5 minus 2 times 180, or 3 times 180, I get 540. 540 is how much they all add up to. 540 divided by 5 is 108 degrees. So each one of these interior angles is 108 degrees. If I'm going to put them adjacent to each other in order to make a circle, I need it to be able to divide evenly into, how many degrees is a circle? 360. Does 360 divide evenly with 108 dividing into it? Well, let's grab our calculator and check it out. It does not. 3.3333, and it keeps going. That's not dividing evenly. Therefore, checking this mathematically, I see that the regular pentagon does not tessellate. No. We can also see it by playing with them. But how often do you actually have a bunch of pentagons laying around that you can play with? Let's look at triangles, squares, and octagons. Do they tessellate? Well, let's do the same thing that we did before. Check out according to the angle measures. Now, hopefully by now, we remember that the triangle, if it's regular, each of these angles is 60 degrees. So, 360 makes a circle. Divide it by 60. Does it go in evenly? Yes, it does. 6 times. That means I'm going to need 6 interior angles adjacent to each other. Let's try to do that and see if it will work. And there we have our visual of the regular triangle tessellating. In fact, there are 6 of them. 1, 2, 3, 4, 5, 6. 6 of those around this point in order to tessellate. How about a square? How much is each of these interior angles? 90 degrees. So take 360, divide it by 90. How much do we get? 4. So I can take 4 of these squares around one singular point, and I'm going to get a regular tessellation. 1, 2, 3, 4. What about the octagon? Well, first of all, do you remember how many degrees is one interior angle of a regular octagon? Yeah, I don't really either. So maybe we figure this out. We can do 8 minus 2 times 180. Octagon is 8. Octa, like octopus, n equals 8. Now you could be doing this along with me on your note sheet. Which of the following regular polygons will also tessellate? So we determined that a triangle will tessellate. Yes. Why? Because each angle, each interior angle measures 60 degrees, and 360 divided by 60 comes out to an even amount, 6. Square? Yes. Why? What did we do? 90 degrees was the interior angle, and 360 divided by 90 came out to 4. Pentagon? No. Why not? Well, 360 divided by 108 came out to about 3.33, not a whole number, right? Whole number, when we divide it into 360, whole number, when we divide it into 360, not a whole number. So what about the octagon? So let's work this out. Octa, oct, n equals 8, like octopus. Octagon, n equals 8. So 8 minus 2 times 180, because I don't really remember the interior angle measures of an octagon, but we can figure it out. So that makes 6 times 180, and that is 1080. Take that 1080, divide it by 8. 135. 360 is what it has to divide evenly into. 360 divided by 135, 2.66666. Keeps going, keeps going. So, is it a whole number? Nope, not a whole number. Therefore, octagon, no. Triangle, yes. Square, yes. Hexagon, like we saw earlier, yes. So, how do we determine whether a regular polygon will tessellate? The interior angle measure must be a factor of 360. So that means when we do 360 divided by one angle measure, it equals a whole number. Divides into it evenly. Tessellations are also found in a variety of artwork. M.C. Escher is one of the most famous artists that used tessellations. Here's a couple examples. Can you identify the figure that's tessellated in the following images by M.C. Escher? What's this a picture of? Some of them are white and some of them are black, but it looks like this is a tessellation of birds. Notice that they've been rotated or reflected to make that tessellation of no gaps or overlaps. How about in this one? This is actually a tessellation of two different shapes. The white ones look like fish, whereas the black ones maybe look like other types of fish or boats? I don't know, but it is two different shapes. The point is, the tessellation is made up of shapes that don't overlap or leave any gaps. Let's look at an example like what you might see when you know what a tessellation is. Some of the angles are given for the fish-shaped polygon in this tessellation. What is the value of x? Well, the fact that it's a tessellation is very important because a tessellation is made from the same shape being repeated over and over in order to make that tiling shape. So if I see where the x is at this angle, it would be helpful to know how much the angle adjacent to it is. Why? Well, because those two angles that are adjacent to each other, they make up this straight line right here. And how many degrees is a straight line? 180 degrees. So if I know how much that angle is that's adjacent to the x, that will be helpful. Well, where is that angle? Right above the fish's eye. In this picture, right above the fish's eye is the 150 degree angle. So that means this angle has to be 150 degrees. So 180 minus that 150 degree angle is 30 degrees. X is 30. And there we used a tessellation to solve that problem. Fantastic.